Hey everyone, welcome back to Faraday Research. It is Wednesday night and I've been doing a crazy amount of testing. So I kind of sat back and I was thinking how methodically how I can go about trying to get a very accurate reading on testing these motors. And I've listened to a lot of guys who are out in the field who are electronics diagnostic engineers that get paid to test devices like this, and it boils down to actually making proper meter readings. Sometimes that can be more difficult than actually building the motor. So what I did was I did a bunch of tests tonight. I'm going to show you my values, and I'm actually going to show you what it actually takes to run this. So let's start with the lights. Okay, I've been using these lights for a while now, and a lot of people are complaining, oh, what's proper power outage, wattage. All right, so each one of these lights has a number on it. That's what the light is rated, it's equivalent to. Okay, so I got four 5.5, so that's 11 watts, and then I got two lights here, they're 9 and 9, that's 18, plus 9 and 9, that's another 18. So I have a total of 47 watts equivalent. Doesn't mean that's the actual watt rating. Okay, that's what they're equivalent to a regular incandescent bulb. That's what all of these lights are equivalent to, is 47 watts. But it's not actually using that amount of power to actually power the device or those lights. So I got my watt hour meter. I got it hooked up to my inverter. Okay, so for this test, what I did was I got one of these cart batteries. Okay, that's 12 volts. I believe 11 amp hour. Yeah, 12 volts, 11 amp hour. Right, so I just got the inverter hooked up to the battery, to the watt hour meter, and to the lights. Okay, they say it's equivalent to 47 watts total, but that's not exactly how much power it actually takes to run it. These are LED lights, they're more efficient, they're built to be more efficient, but the luminance that you get off it is equivalent to 47 watts. Okay, so before we get into the first test, if you haven't subscribed to the channel, bottom right hand corner, also give me a thumbs up for this video. This video is going to have a lot of very important information that's going to help you differentiate between using an inverter, running lights, power versus actual real watts that's being used in it. And also your motor itself, it runs different. I'll get into that later, but I'm going to tell you how to kind of differentiate between the two different methods of lighting lights. If I hook up the motor directly to the lights, it's a totally different set of math compared to the lights hooked up to an inverter that runs at 60 hertz. Okay, you're using a DC power source. So ultimately, in the end, what I wanted to find out tonight is my motor over unity. And believe it or not, I'm going to leave the results for the end. So I'm going to go through everything tonight, and you can just take notes and watch what I'm doing. So you have to understand the two different methods of running the system. One, running the motor directly onto the lights with no capacitors, nothing. Directly from motor to lights. Okay? So you have to know the wattage going into the system and what's actually going out of the system. And I was actually able to get a very accurate reading what I'm actually doing. So you'll see the results. I'm not going to give it away. I'll leave it for the end. So first test, we're going to find out what really these things draw in wattage versus what the rated value of what they're equivalent to simulating. So they say all these lights together, 47 watts. Well, it does not take 47 watts to run these lights because they're LEDs. They're not incandescent bulbs. So I'm going to flip the switch on for the inverter, and I'm going to show you exactly how much power it actually takes to run these lights at full power. Alright, so let's do that right now. I'm going to turn it on. Okay, you can see the lights are fully illuminated. So we can see the value. It's telling me these lights are taking 18.3 watts of power. Alright. Current rating, 150 milliamps. 148, it was at 150. The battery's kind of going down. Alright, so that's low. So it's 18.3 watts to light up these bulbs completely. Alright, I'm going to shut it off because I want to show you some figures. So now we know that it takes 18.3 watts to run these lights. Alright, that's the true watt rating for these. So I wrote it down here. So let's take a look at my piece of paper here. Alright, hopefully you can see that good. Alright, so we got, it's putting out 120 volts at 0.53 amps, which we saw on the meter. Alright, so 120 volts. This is AC voltage now, not DC. This is AC voltage. 120 volts times that 0.153 amps works out to 18.36 watts, which we saw on the meter. Okay, it was 18.3 watts. Now, if we go to the battery, I'm not going to actually hook it up. It's no point. But I wanted to show you the actual watt meter, what it actually takes to run it. So now when I took my amp meter to the battery, turned the system on, well, I know the battery's got 12.5 volts. All right. Now we're running DC now. We're not AC, we're in DC. So 12.5 volts DC, okay? Times that by, it took 0.58 amps, so just over a half an amp. Or sorry, 0.58 amps, so 580 milliamps. That turns out to 7.2 watts. So that means it took 7.2 watts of this battery to produce 18.3 watts of AC power at 60 hertz. Okay? Now you got to understand, this is at 60 hertz. All right? So, in actual fact, if you look at between DC and AC, AC is half the voltage of what DC is. Right? So, you can almost kind of look at, this actually being over unity on its own, because it only takes 7.2 watts of DC power to run 18.3 watts of AC power. So it seems like a power game, but it really isn't, because AC is basically DC divided by 2. So 18 divided by 2, 2 8s are 16, 2 9s are 18, so it's really 9 volts AC in a DC current. I know it sounds kind of confusing, but you're trying to compare, apples and oranges, because they're two totally different things. One's direct current and the other one's alternating current at 60 hertz. So this is where I think a lot of people get confused in power readings. So I'm very comfortable with this. It seems very accurate to me. So really it takes, in DC voltage, 7.25 watts DC to power an 18.3 watt AC load. Okay? So if we can agree on that, I'm good with that. It seems pretty good. I'm still going to try to get this tested by this laboratory, and it's about 30 minutes for me. I'll get into that later. Anyways, that's another story all on its own. Okay. So that's that. Now, the second test I did was running the pulse motor, or the RPG I call it, reactive power generator. Okay, now I would run it directly from the motor to the lights. So I'm going to disconnect this white cable here, and I'm going to hook it up here. All right, now I know this will not power my lights fully, but what I wanted to do was get an accurate reading of my voltage going into the system versus voltage coming out of the system to run the lights. Don't worry about how much voltage I'm putting in the lights, okay? So the main thing was I wanted to see how much power is going in versus how much power is going out, okay? But now we have a situation here where the dynamics change because I am no longer running at 60 hertz. I'm running at a different hertz level. Now, if this was running at 60 hertz, then these lights would be powered up efficiently enough that I could run them completely at that current. So that's not the case here. Mine run at a higher frequency. Okay, that's why I'm able to put so little current into this and light these up, is because my frequency has changed. Now, from what my last test I saw on the scope meter, it was 127 hertz from, say, 60 hertz. So these things are flickering at a faster hertz level than normal. Okay, 127 hertz now makes this thing a lot more efficient, so I can do the same work for less because I'm running it at a higher frequency. Okay, so let's go to the next page. I'll show you the actual motor running, but I want to show you what I got. So I put the voltmeter right up to full. All right, so I had 32.9 volts DC going into the motor at 111, or sorry, 0.11 amps, or 110 milliamps, basically. All right, so 110 milliamps going in. So if you times 32.9 volts times that by 0.11 amps, means I was putting into the motor 3.619 watts DC, not AC, DC. Okay, now here's where it gets interesting. I did the meter readings on the output on here, coming out of here. Okay, so now I got 33.7 volts DC. It went up. It was 32.9 here. Now it's 33.7. I had 0.11 amps here. Now it's 185 amps. It went up as well. So my voltage went up and my current went up. So it went up about 70 milliamps, 75 milliamps increase. All right. So I went up about, 75 milliamps. So now if you times 33.7 times 0.185 amps, I was putting out 6.2345 watts. That means I was putting out twice the amount of power that I was putting in. So from my meter readings, what I'm getting, this thing is over unity. I'm getting twice the amount of power out that I'm putting in. It's right there in the numbers. I can't lie. So there it is. Here's a better little screenshot of it. All right. Now this is all in DC. Okay. This one here, it was an AC, but you're converting a DC load into an AC current. So it takes less DC wattage to power an AC wattage. It went from 7.25 watts DC to 18 watts AC. So right there, that's over unity. If you want to look at it like that, it really is. But it becomes inefficient in the fact that it's running at 60 hertz. It's actually drawing a lot of current. So this is where the problem occurs, why these things are not efficient, the inverters. Off the battery load, look how many amps it's drawing. It's drawing over a half an amp, almost 0.6 amps. That's a lot of load to come off a battery. And that's why it sounds good here. You know, you got 7.25 watts DC going in, but people don't understand what kills a battery. Amps. And that's exactly what makes this system inefficient. it's pulling over a half an amp. That's why if it was, say, down to, say, like 11 milliamps or say 110 milliamps, that's a lot better than a half an amp, right? So you're going to kill a battery off pretty fast with this. It won't last. It'll die. Now, I can achieve almost the same kind of values, but a lot better, because this machine runs at a higher hertz level. Frequency is everything. Tesla talks about energy, frequency, vibration. Okay? So you can put in a lot of power, very little current, and get higher wattage output, because my frequency, everybody, frequency is higher than 60 hertz. That's why I'm getting the ability to only put in, I'm putting in 3.6 watts, and I can almost light all those lights up. Is because the frequency. I'm running at a higher frequency. I'm putting in 3.6 watts in, and my motor is going over unity to 6.32 watts output. So I'm putting 6 watts in. I'm able to light up all those lights up because of the frequency. You see what I'm getting at? If you run at 60 hertz, you got to put a hell of a lot more current in to do the same job. You get it? If you're running at a higher frequency, you can do the same job with less current. If you're running at 60 hertz, and say, not like this thing, I believe, is running about almost 130 hertz. This is running at 60 hertz. It takes a huge amount of current to run it. 0.58 amps. See what I'm getting at? So, you know, like, you're trying to compare apples and oranges here, because it actually is. It's very confusing to a lot of people. I understand that. But now I totally understand what's going on. And the best part about it, this was the one that really got me, was my machine is over unity. And the reason for it is because I'm running the machine at a higher frequency. Okay? That's where it all boils down to. Okay, you don't have to look at what your actual output is. It's the ratio of what you're putting in versus what you're getting out. I don't care if I'm making 18 or 20, 50, 100 watts. I don't care about the output. I care about the ratio of how much power I'm putting in the system versus how much I'm putting out. Okay? So, based on my calculations, my machine is putting in 0.36 watts in, and I'm getting 6.2345 watts out. I'm getting double the power out. This machine is over unity, and I'm very confident with the readings that I did. If I go to this guy's laboratory and he does a test on it, it's probably going to be in the same ballpark. So basically a 2-to-1 gain in power. I'm getting twice the amount of power that I'm actually putting in. So, yeah, it sounds very complicated. You have to distinguish between hertz level versus battery converting DC power into AC power, back and forth. So I tried to separate the two scenarios. All right. So if you have to go back and look at this video again, do, because it might take a few tries for you to actually understand it. It took me all night to try to figure out what I was actually doing, but now it really makes a lot of sense. And it all boils down to frequency. So if you run your system at a high frequency, your efficiencies go up. The amount of current that you're going to need to power the motor goes down. Put the voltage up higher, but now your current doesn't have to go high anymore. It'll actually go lower. And also now your motor's running at a higher frequency. You're able to power a higher load at a higher frequency to do the same job for a lot less. So I don't know if that made any sense to you guys, but hopefully it did. I think this was kind of a breakthrough video for me, because I was actually able to prove it in my meter readings versus how much power I was putting into my pulse motor versus what I was getting out. So by the looks of it, I'm getting twice the amount of power out that I'm actually putting in. I don't care really on the load. All I cared about was the current coming out of here and the voltage DC. All right. And the why I got this gain increase is because of the frequency. That's the key to your system to go over unity. You want to make your system go over unity, get that frequency way high. You know, if you want to run, say, like a load, you want to run something. So now I know what I've got. I know what I can do with it. Now it's a matter of how to utilize what I have. And now that I know what to utilize and where the strengths are of this motor, now I can go forward and say, okay, well, I want to charge batteries with this. Well, now I know I can put out about 6.23 watts of power DC at a high frequency into that battery to keep that battery charged. That's a good thing because I'm only putting in 3.6 watts, right? So there's over unity right there. So if you have to run devices at 60 hertz, you would have two sets of batteries. You have one running the inverter while the other is getting charged. When this guy charges back up again, you swap the batteries, and that charged battery is now running your 60 hertz load, which is an inefficient bullshit system that we've been using for 120 years, and it really should be changed because we're using the wrong frequency. We're using a parasitic frequency of 60 hertz. It should be 200 hertz. The efficiencies of our lights, our power system, our power grid, power everything would transform overnight into a very highly efficient system. So anyways, I'm just kind of rambling now, but questions, comments below. Don't forget my links for my description, Patreon, my PayPal donate. I hope I helped you guys out understand what's going on with this. And now I'm really happy because I got it in paper that I know my system's over unity. So now if I go to the lab to get it tested, I'm pretty sure my readings are going to be pretty accurate, pretty close to this. And yeah, even if I get a couple of points above over unity, hey, that's a step in the right direction in my books. But from what I could see, I'm making twice the amount of power what I'm putting into the system. So yeah, I like what I see. I'm happy how the things went tonight. Give me a thumbs up again, and we'll see everybody soon.